Hi, I'm Josh. Welcome to this video, which is on the cross product. The cross product takes two vectors, a and b, and creates a third vector that's orthogonal to both of them. We can create this orthogonal vector by using the dot product. What we know from the dot product is that if two vectors, a and c, are orthogonal to each other, then their dot product is 0. By creating a vector c for which a dot c is 0 and b dot c is 0, we can find our definition of the cross product. For more detailed proof, please see the supplemental video. This vector c is certainly orthogonal to a and b, but we can take any scaling of it that we want. But by taking a scale of only 1, which is the vector c itself, we actually satisfy two things: the right-hand rule, and we know some very specific details about the magnitude of this vector. The direction of this vector that we created follows the right-hand rule. What this means is that if you had vector A here and vector B here, the third vector is coming this direction. And the way we figure that out is we take our fingers and put them in the direction of A so that they can curl towards B. And then the direction of our thumb points the direction of C. See how if we put our fingers pointing towards A and did the other direction, it would be wrong. Or if we did it with our left hand towards A and curl towards B, it would point into the board, which is wrong. Another way of figuring out the direction of the right-hand rule is to make a pistol grip with your hand. Then point your thumb towards the first vector, your finger towards the second vector, and the direction of your middle finger is the direction of the cross product. So in this case, it confirms again the cross product of A and B points out of the board. Additionally, the magnitude of the cross product has direct correlation with the parallelogram created by the two vectors that created the cross product. So if A was this vector and B was this vector, the parallelogram, which actually the area of which is the magnitude of the cross product, is this. So you take B and you transpose it up, and A and you transpose it over, and this area right here correlates to the magnitude of C. And we know that the magnitude of a parallelogram is just AB sine theta from our trig classes, and we can confirm that this is equal to the magnitude of our cross product by taking the definition of our cross product coordinates and plugging it in to the definition of our magnitude. And then by expanding, we find that indeed the area of the parallelogram, that is AB sine theta, equals the magnitude of A cross B, which is also AB sine theta. So let's do another example with numbers. Let's say vector A is 1, 2, negative 1, and B is 3, 0, 4. To take A cross B, we need to figure out all of the components. So the first component is C1 is going to equal 2 times 4 minus 0 times negative 1. The second component is going to be 1 times 4 minus 3 times negative 1. And the last component, C3, is going to be 1 times 0 minus 3 times 2. So then these are just, the first one is 8 minus 0, which is 8. The second one is 4 plus 3, which is 7. And the last one is 0 minus 6, which is negative 6. So our cross product, A cross B, just equals the vector 8, 7, negative 6. This great function has applications all over physics, math, and engineering. I recommend checking out the supplemental material in the JOLT and other places online to find out some more about those applications and some practice problems.